So for our first lab of the year, we're going to use these cheap squirt guns, and we're going to try to figure out how fast they shoot out water. We're going to use the ideas you've learned in your previous physics classes in order to accomplish this. It's not an easy lab to do. There's some sources of error that have to do with pushing this trigger at a certain velocity, that have to do with how many pumps you actually do. So it's going to mostly be a fun lab and to try to link the earlier knowledge to our current knowledge. Let's see what we can do. So in class I treated this as an open inquiry lab, and I gave you a bunch of equipment and asked you to come up with a procedure. The only thing I think we really can do to start to answer this question is to treat it as projectile motion. In other words, if we know how high we held the squirt gun and we know how far it shoots, we should be able to backtrack and figure out how fast the water was coming out. This shouldn't be that hard a projectile motion lab to do. It's a horizontal launch. The math should be relatively straightforward. But when you start to play with the squirt gun, you realize we have a problem. Rather than a discrete landing zone, like say they're all landing here, we have some drops that land here, some drops that land here, and that means that not every drop of water leaving the gun is going at one speed. So how we get a single answer for this problem becomes a little tricky. Let's look a little more at the trigger of the gun and see if that gives us any clues. The problem seems to be that the trigger is a pump. So the speed at which you press this pump, how many times you pump it, they all seem to contribute to essentially how fast the different drops are going. That's why you can have a variety of speeds within a single pump. So in order to keep this lab doable and to get some sort of meaningful data, we're going to have to be very careful about how we pump that trigger. The best thing I've come up with is this. I have the squirt gun mounted on a ring stand. I've squirted it a few times to see where it lands, and I've got meter sticks running along the bench. In the place where most of the drops land, I've got paper towels, which will let me mark kind of where the drops are going. I found that if I just do one pump relatively quickly, I do see kind of a bell curve distribution where a few drops go really far, a few drops go not so far, but the majority of the drops are kind of in the middle. And that's what we'll look for, which is kind of like the average velocity of a drop. So here's where my water was hitting the paper towels, and you can see most of the marks are kind of like here. And that's at about 2.58 meters. To do a projectile motion problem, we also need to know the height of the gun. So mine was around 28 centimeters high. We're going to take these two pieces of data and we'll see if we can figure out kind of a middle of the road velocity for drops coming out of this squirt gun. Despite all the flaws in this lab, we really can solve for where most of my drops were going, where the biggest splotch was on the table. I found that to be 2.58 meters down the table from the tip of the gun. I found the gun to be 28.3 centimeters high. So we can solve for how fast the water drops were leaving using projectile motion. I hope you've learned this in another class. I am going to make some videos available for you if you'd like to review it. It's not a really big focus in this class, but the idea of keeping horizontal and vertical separate to solve problems is important. What I ask my students to do first usually on this type of problem is to specify a reference frame. You can pick any place you want, but I like to call the origin directly under the launch point on the ground. That makes this 0, 0. The 2 points we care about for the problem are the launch point, XO, YO, and the landing point, XY. Because of where we picked our origin, that means these 2 points are on the X and Y axis. So XO here is 0, and its YO is 0.283. Remember, we have to use standard units in physics always. That's going to be really important in this class where we start dealing with some more complicated units. X and Y. x is obviously 2.58. And since it's on the x-axis, y is 0. So that really organizes our data. I usually then ask students to make a table. This is how I like to make mine. Horizontal, vertical. And I just kind of list every variable you could have in projectile motion. That helps pick which of the 3 equations you want to use. So we could have an x original, we could have an x final, we could have a VOX, we could have a VX, we could have an AX, and of course we could have time, which is shared between both of them. We could have all the same things in Y. So what do we know? Well, we know that XO apparently is 0, and X is 2.58. VOX is what we'd like to know. We don't know anything about the final X velocity. We do know that there are no forces acting horizontally, so AX is 0. Let's play again. We know that YO is 0.283. Y is 0. VOY, because the gun was launched horizontally, is 0. VY we don't know about. AY, since we're acting under the influence of gravity, minus 9.8 meters per second squared. All right, so once you have all this information in front of you, it becomes pretty simple to pick the appropriate equations for solving it. Time is often the link between the two, so we usually want one of the motion equations that has time in it, either the ones with x and xo or v and vo. Since we have distances here, we're going to want the one that's got distance in it. So we'll do 2 versions of the equation. An x version. So 2.58 is 0 plus VOXT plus 0. So we can't solve that anymore, of course, because we don't know what VOX is and we don't know what time is. But we know from projectile motion that the time it took to get here is also the time it took to get here. So we can use all our y information to solve for time. So let's do that. So our final y is 0, our y naught is 0.283. This whole thing is 0 plus 1/2 minus 9.8 t squared. So this is solvable for t, and then we can plug in up there. So I'm just going to do it. 0.240. So with that information, we can now plug in up here and solve the problem. So divide by 0.24. So 10.75 meters per second. Is that a reasonable answer? If we squirt this, do we think it would go 10 yards on a football field in a second? I think that's fairly reasonable. I kind of blazed through that. If you are interested in more projectile motion, just as a review, check the Flickr album. I will have a couple of videos up there just if you want to review it. Again, projectile motion is not a big topic in this course, but I feel like setting up a problem organized, keeping x and y separate, it's kind of a good thing to review.